Okay. You understand? Okay. So we're gonna record the the slides and whatever you say, and therefore if you don't want to appear, don't talk. Right. Great. So welcome everybody. Here and at home and at your workplace. So I'm David Rios. I work at Ethermat here, and together with Roy and a couple of persons that I introduced in a minute, we are organizing this thing. So Roy is at CUNEF. By the way, this is a image generated with DALI, which is one of the subjects that we're going to talk about, generated by Roy, based on three things: large language models, Madrid, and surfing, right? And well, basically, the idea is that I don't know how are you using it, but well, we are starting to use it in various ways for our research. For example, many of us, before programming something kind of complex, we give some instructions and prompts to ChatGPT or whatever you prefer, and get some code. Or we've done all very lengthy searches, basically doing manually on cancer and etc. Now we do it with ChatGPT. So we are doing it ways that are usually appearing in the press, etc. But now people are starting to do. I mean, we'll see things like transformers do Bayesian or learn Bayesian inference, or transformers as statisticians, etc. So we were kind of intrigued about that kind of thing. There's also, I mean, there's like some very cool things, but if you read some of the stuff, there's also some dubious work, research-oriented work on that. So that was our idea. We wanted to first get acquainted to these kind of things that we've been working on it for a while. But also we wanted to sort of push a couple of things that we believe will be of a lot of interest, which are, first of all, pushing forward Bayesian methods in this area. And the second topic that is of interest for us in this here at ISMAT is the security of those models. So these are our main goals. You can make, Arkan, what's your name? Yes. So you can make questions whenever you want. We want to, and the people that I mentioned in a minute are more like facilitators for the discussion. So I don't know, we are not like preachers, or we are not evangelists or whatever. So that's working. So working. Yeah, okay. So first of all, a couple of since Autonoma is so far, and if you come by train, as I do, These are a couple of reads that you can, to get acquainted with this, with the sort of, let's call it light, broad topics about LLMs. So we have in this sprint, that's an image from this paper, a survey of large language models. And that's an image from when they released the first version. That was a few months after the release of ChatGPT. So that's 23 November. Very quickly, there were some reactions. And so that was the previous image. That's what has happened until the end of last year. So you can see that there's lots of, it's a real sprint. Okay. It works out. Okay. Thanks. So also there's a lot of hype, the AI hype that we are discussing. But particularly the hype is probably coming from, the hype of the last months comes from these LLMs, right? And I'm just taking a couple of examples. One is from policy. Last, I think it was about a month ago, the Parliament approved the European Artificial Intelligence Act. And the last month, it was basically a discussion of what to include about generative artificial intelligence in the act. Sorry. The other thing is the second example is Biden's executive order on safe, security, trustworthy artificial intelligence. And one of the orders in that order was that in a few months, the NIST should develop a risk management framework for generative AI. They already produced a framework for AI at large, which is not very good, by the way. But they have been required to provide this. And even last Friday, the president of IBM Research went to visit the president of the Spanish government to discuss about large language models, basically. And in science, I just put four titles of papers of in the areas in the space that we work more. We as in ISAMAT or Data Lab or whatever or PUNER. Transformers can do Bayesian inference. Transformers as statisticians, learning the language of time series and towards evaluating that, and that motivates a lot of discussion, and that motivates our interest. Just a example of the things that we'll be doing. That's an example from a paper. One of the examples from a paper that we did a bit ago. And basically, that's an example on sentiment analysis. So basically, we plug a text. In this case, our movie reviews, and the machine needs to forecast. Needs to assess whether the sentiment in this is positive or negative. So based on a few examples. It needs to predict this kind of thing. So I think this kind of summarizes quite a lot what we are going to see in the next days, right? So today we're going to focus on this, which was, let's say, ultra cool, let's say like 5 years ago. By the way, that was an invention of the late 90s, which was discovered. This is, for example, at the basis of Siri, for example. And with this type of models, actually with a couple of layers of LSTMs, so Victor was able to get an accuracy of 82%, right? A simple transformer, which is basically what Roy will explain next week, provides quite a bit of improvement. Right, 87%, and Roberta, which is a large language model based on the T is for transformer, but it's basically a pre-trained on a very large volume of text in English, and then fine-tuned to cope with this specific domain. So we were able to get a 94% of accuracy in the test part. So that's kind of the sort of travel or journey that we're gonna follow. And I mean, it basically indicates that we can do things that relatively recently were very difficult, now become like a commodity. So this also talks about a paradigm change in natural language processing. So I put here from predict learning, and I should have written, I mean, to be logical, I should have written in the deep learning area, but on purpose, I just have to sort of attack a little bit. I changed it to statistical level. So like a few years ago, quite a few years ago, this area was basically, well, it was predominated by the ideas of one of the genius of the last century and this century, which is Noam Chomsky. But basically, it was a sort of very language was a set of elements and rules to be combined. There was the context-independent grammars due to Chomsky, and it was it was closer to artificial languages like programming than to natural ones. And now the basis is language as probabilities of words sequences, basically computing frequencies of words and n-grams, etc., and it's closer to natural language. And the state of art is based on transformers. And now actually is almost a commodity, and like vision. Like I always say that these were the robots that we used to develop until we ran out of money, like 2 or 3 years ago after the pandemics. And when we started this, it was like 10 or 12 years ago. We were doing these kind of language things, but it was even if we were working with the sort of best guy in that at that time, which was Bruce Wilcox, but we were performing really. I mean, it was okay, but nothing spectacular. But now, I mean, it would be like a piece of cake. So if somebody wants to revive the project, it would be he or she would have a much easier life. So these are our two objectives. The first one is short term, so we're going to discuss or facilitate discussions on this. But the medium term is, I mean, at least for us, is more interesting. Is try to create some kind of working group on Bayesian issues and security issues, which are quite important at the moment. And that's the schedule. So basically, the first day today we are going to talk on recurrent neural networks and deep neural networks. Then the sort of thing that changed will be the objective of next week by Roy Naveiro on transformers. Then you appreciate the T here is a transformer. So Carlos Meixide will lead the discussion on GPT. That's one of the examples based on transformers. Then Victor Gallego, he will talk about, I mean, once you have this generally pre-trained general purpose, let's say, how do you fine-tune to whatever aspect you want through what is called reinforcement learning with human feedback and some other variants and he's a specialist on that and is doing quite a few projects on that in the real world. And finally, I'll talk. I mean, the last day we'll talk about these issues that we want to pursue in future in as far as research is concerned. So one change is because of traveling issues, we have changed this one, right? And also know that we will alternate from Ethermat to UNEF just by EC instance in the Center of Computing University campus. Some logistics. Well, all this will be is being recorded through Zoom, and if you we have done a mailing list, and if you are not in the mailing list, as in my case, we must ask Roy, and we'll put this GitHub place with slides, videos, and so on, some code from time to time. And if you need any other questions, just to ask Roy and myself. Okay, I don't know if you want to make any questions or comments. Okay, so I'm going to start. So these are the key ideas for today. So basically, LLMs are deep neural nets, and hence we need a brief recall. By the way, some people are super experts. Some are not so expert, so bear with us. We want to sort of put, I mean, like provide a very a quick ground leveling approach. So yeah. The other key idea is that LLMs are basically recurrent neural nets. Hence, we need to provide a brief recall of those nets, and in particular LSTM and GRU, which are what we talked today. Another important thing is that DNNs essentially process numbers, and basically we need to provide a brief recall on how to convert text into vectors. Basically the key idea of embeddings. The evolution of NLP that we just mentioned, and some hints on Bayesian nets, nets that will just briefly touch upon them today, and we'll recover them on the last day. Well, some of the readings, a couple of papers that you can read on the train, a more sort of computer science oriented book, right? And a little slightly more mathematical book. And yeah, this is quite good, as from minute 8:55, if you want to recall the materials. Okay, so what we're gonna do is start by doing a sort of quick journey from neural nets to deep neural nets, right? And basically, that's a stuff from the 70s or 80s. So basically, this is a picture of what would be a neural net. Basically, there's an input of data. These are numbers, right? These are processed in a particular way. So first, there is a linear combination at each of these nodes or its cells. Then it's non-linearly transformed by each of these cells. So this was here. And then there is a further linear combination, which is what is output, right? So we had an error, a Gaussian error. This nonlinear transformation originally was this logistic function. So basically, we have let's call it a sort of combination of traditional statistical models. So we have a linear model in the betas and a nonlinear in the gammas, right? So that became in trend, let's say in 1990, right? Around because of these type of theorems and related ones. So basically, there's this Savinkov theorem, which is quite famous, which says that any continuous function in a certain region may be approximated by these types of functions when this function is sigmoidal, right? And for this, m needs to go to infinity. So the type of proofs are not constructive, and therefore this puts a problem, which is how do you choose the architecture? In this case, how do you choose this, which is quite important. So training basically is given that we have Gaussian noise, Basically, we do it by least squares, right? We use gradient descent, and we use back propagation to estimate the gradient. I'm putting here a gradient back propagation from one of my favorite books, which is there. And I put it because this idea of gradient flow is quite important to understand several of the things that we're going to tell later on. But basically, I mean, the intentions, it doesn't matter. The details are not important, but basically, there's a flow backwards. So there's a forward pass, right? And then there's a backward pass to update the gradients. So at the end of the network, there's a first computation, and then this is flowing backwards through this loop till the end, and then and basically this is the chain rule. Right. But this flow backwards, this is quite important, and it will appear. It will explain some of the ideas on recurrent neural networks, etc. So as in in other statistical domains, so quite quickly people realized that we should introduce ideas for regularization to sort of regularize the behavior of the model that we feed. And for example, one idea is to use what is called weight decay, which is expressed like this, right? Which in statistics is called ridge regression. But the same type of ideas, same type of foundational requirements, etc., etc. And that this will be quite important, the vanishing gradient problem. So we said here that we compute this backwards, and the idea is that well, that is the derivative of what, and basically the idea is that if we stack several of these layers, then the gradient gets smaller and smaller. This prevents from learning, and well, this leads to a problem which is quite relevant, especially relevant in recurrent neural networks, which is the vanishing gradient problem. Early stopping is quite important concept. And then some ideas, just a pinch on Bayesian analysis of neural networks. That this is a paper which was before, for example, Danny was born, for example. That's quite old. But basically the idea is we put priors on the previous model, and we need a way to compute, assess the posteriors and the predictives, right? And the sort of interesting idea is that interesting point to make, and that we will come back to this, is that in this case those priors are interpretable. I mean, we are still in a shallow neural net. This has several benefits, especially in relation to choosing the architecture, selecting the architecture by things like hypothesis testing and so on. So that's we can do these kind of things to get the distributions, the predictive distributions. I put in red here a fixed architecture. So we are assuming here that the number of cells, the number of nodes in the hidden layer is fixed, but we can extend it to sort of uncertain architectures, and that's a sort of a strong point in this. You can extend this to classification with using, for example, a multinomial likelihood. So you can cover, and you can then nonlinear autoregressions, non-parametric regressions, and so on. So many things then. Okay, so we move from here to here. So basically we stack several of these layers, and then there is this nonlinear processing, etc. And that's these are deep neural networks. And the theorems are slightly different, but there's approximation theorems. Like, for example, any integral function can be approximated by fully connected neural networks as the depth goes to infinity. So before it was the width who was going to infinity. Now you can, you can pile this, right? And if you control, you can control it. The depth goes to infinity with the width bounded. So you get these approximated theorems, right? And I put this in red because, like in the 90s, mid-90s, people tried to stack all these layers, nonlinear layers, but this led to the vanishing gradient problem that I mentioned before. With this, among other advantages, this was mitigated. So the ReLU is, initially we were using this sigmoid and tanh activation functions. Now with these ones and variants, we avoid the problems of vanishing gradient. And also it has the computational advantage of being much simpler to compute it's much faster to compute the derivative in this case.
David, my apologies, if you allow me. I am, this comes, of course, mainly out of the paper that you go for.
No. This comes from somebody else.
But I mean, some of the formulas, maybe it's another paper. But I just wanted, to ask a little question. I was a little bit surprised, by the inclusion of time series, especially nonlinear time series, because my idea was basically that even in the case of, for example, Markov switching regime models, for example, or self-exciting threshold auto-regressive models. You can hear me well, yeah. So basically, the main problem, with these models, both with star or zeta or Markov switching regime models, is that essentially you have only two regimes. And so basically, right? Essentially you have two regimes, right? So for example, if you are trying to model, for example, an economic scenario, then you have one regime, for example, in a zeta model, right, for recession.
What's in there?
For example, in a zeta model, for example, self-exciting threshold autoregressive model. So for example, if you're trying to model an economic scenario, so then essentially you have two regimes. One for recession, which is of course, which has a much steeper decline, right? And then, for economic recovery, which is of course, much smoother in mathematical terms. So then, the idea that I had, about deep learning is that by means of deep learning, we could precisely, be more flexible insofar that we could allow, more than only two regimes, because of the inherent flexibility of, that hidden layers allow us. So maybe you would like to comment a little bit, on this idea, on.
But I think to handle this, you don't need to go, into the deep. You can handle this with state space models. They are capable of doing that kind of things. You don't need to. I don't know. You don't need the stationary things, and so that's sufficient. But if you need to incorporate nonlinearities in this evolution, then you need to incorporate this.
Deep learning science, maybe. Okay.
Thanks. So training is the same idea. The problem is that the size. The number of terms is so big that it doesn't fit in the memory, for example, and we need to go through to a stochastic gradient descent, which basically you random sample a mini batch, you approximate the gradient, and then you do this kind of update. The same kind of update. Okay, and the idea is that if you choose properly the rates, then you have a guarantee that SDG converges. Right. you can actually, there's several variants of HGD, right? And well, that's a sort of kind of quick introduction, right? Now we're going to start with the proper topic, which is neural networks for sequence processing, right? And the basic idea is that fully connected neural networks can approximate any function, as we mentioned in the couple of approximation theorems that we mentioned. But training can be super slow and may require lots of data. And therefore, in various domains, specific architectures, not the generic one, not the fully connected one, have appeared, have emerged. And in particular, in NLP, recurrent neural networks and its successors that we shall be seeing have appeared. And more, I mean, the problem is actually more general. It's beyond NLP. It's more general in sequence processing. That's a way to go forward, right? I mean, beyond language. That's now people are using this for example, for video processing, etc., but also for molecule processing in chemistry, drug discovery, etc. So I mean, it's more language, and of course for time series, for old style time series. I mean, this is the old time style, but you can actually use for nonlinear autoregressions. But as I said, we can go better with recurrent neural networks. The idea is these are the sort of key ideas that I mean, they are specialized for sequential data, and this could be number, words, etc. It can one problem with fully connected is that I mean, one advantage over those is that we can process much longer sequences, right? One thing that we'll discuss the next day is that it's amenable to parallelization. So what we'll see today is not so that parallel, but transformers are quite parallelizable, right? The other core topic is that each cell, each node will have one or actually more internal memories, hidden information to store. So that allows, as we'll see in a minute, I mean the importance of memory in language, and there's myriad of applications. I put here some of the applications in language, but in red, image, video, proofs in mathematics, statistical methods, molecular description, drug discovery, etc., etc., etc. Okay. So two core concepts. The first one is recurrence and computational graphs. That's for Luis Tomás especially, right? So in dynamical systems, that's a concept quite used. Recurrence. So basically, and here is the kind of concept that we're going to use is this idea of something which is being input to update some kind of hidden state, and this is there's a recurrency. And if we unfold the computational graph, we get something like this. So basically, what we are going to have is something that we are going to make inputs at each instant. There's going to be a hidden state which takes into account the previous state and the current input, etc. And most of the times we'll use this hidden state to perform useful things, predict the next word, etc., etc. And the other core concept, basic concept, is working with text data. You have a couple of, if you want to read more, I'll just basically, for text, we can interpret it in I don't know, it's a sequence of characters. It's a sequence of words. It's a sequence of groups of n words, right? And basically, we need to convert, as I said, this into numbers, right? And basically, we need to make tokens, chunks, and convert these chunks into vectors, right? Sorry. We can segment text into words and transform it into a vector or characters, etc., etc. So, I mean, the kind of thing that we're going to do is we have some text we had before, like the film reviews. We decide to use as tokens the words, right? And then each of these words with a process, an embedding process, is converted into a vector, which can be processed by the network. So there's various ways to convert one is one-hot encoding, which is basically you give a unique integer to each word. I mean, typically, I don't know, in a sort of bunch of text, you decide to work with the 5,000 more frequent words, for example. So anything which is not those 5,000 words you discard. And then you create a word, for each, you associate to each word a vector of zeros except one for the word. This is sparse and high dimensional and forgets also the order. Right? And then there's word embeddings. Basically, you create dense word vectors, and it's in more low dimensional, and you can either join it, learn it jointly with the main task is something which is called the embedding layer that we'll mention in a minute, or sometimes you pre-compute it on pretend embeddings, like there's something like word2vec, etc., which some people took the work to convert. I mean, have let's call it a dictionary, like says. A student is a vector of dimension 6 with these numbers. Just to, as an example, I mean, the type of things that, the type of tasks that are used is, for example, I don't know, we have 5 words, so 5 gram, right? And we remove and then we try to predict the one in the middle. Or we try to predict, we have 4 and we try to predict. And by this, I mean, and we have the sort of the truth, and then, well, we can implement a learning process like this. For example, BERT is trained with 300 billion tokens and to predict the next word. So, these were 2 core concepts, and now we want to recurrent neural networks. So basically, the idea is that I mean, they appear to process sequences in different length, of different length, and they have. I mean, recurrent means that they have feedback connections, and the idea is that I mean, most of the work until they appear basically refer to one-to-one, right? So we had one input and we had one output, but now in a number of problems, we had to handle things like from one to many, like for example in the image caption. So we have there's an image, a picture, and you want to give a caption. So, right, for example, had to do a project a while ago on that. The project, the example that we had, we showed in the beginning is a many to one. So we had this description of the picture, of the movie based on text, and we had to say whether that was a positive or negative. And in machine translation, for example, you have a many to many. So you have a sentence in Basque, right? And you want to translate to French. So there's a bunch of words in Basque, and you want to get a bunch of words in French. Okay, so that's the computational graph of a recurrent neural network, right? So you can see the recurrency. So there's going to be an input to something, and this is going to process it. And there's going to be a hidden thing, right? And the processing, it takes into account the input and the hidden state. We unfold it, and that's how it goes over time, right? And that's sort of interesting to point out. I mean, one critical issue in language, and why these things are going to, why are these relevant? For example, there's short-term dependencies in language. For example, I don't know if I tell you the clouds are in the, you'll probably say in the sky. So today is quite clean. And this refers to a short-term dependency. So these are two words, and this is quite related to this one, and you can predict. I mean, or a very likely word in this term would be sky. But there's also long-term long-term dependencies which are quite relevant. So we have Mathieu here. So Mathieu would tell us, he speaks a lot, right? I grew up in France, blah, 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 blah. I speak fluent, and you would expect French, right? But I mean, the key thing is that 5 minutes ago, Mathieu told us that he grew up in France. So these are the first words that he told us, and blah, blah, blah. There's a long-term dependency here. So we say that very likely he speaks French. So we complete this based on information which was quite early in his speech. So the first model of this was Hellman's, right? So the network updates the state, and basically that's what we were. I mean, the graph that we had before has this aspect, and he chose, for example, the hidden state is updated as a nonlinear transformation of the hidden state at the previous time and the input. And then, as I said, sometimes, you will use this hidden state to perform, I don't know, to predict the next word, for example, and you apply some kind of. A very important thing is that the weights are the same over time. I mean, they are updated, right? But they are reused, and basically this helps for two things. The number of parameters gets much smaller, and you can learn patterns independently of the position, which is a good thing. This is the unfolded graph, the same thing as before, but now taking into account that we are going to use this to you are going to use this to predict whatever. That would be the ground truth, and there's a loss, and then we try to minimize the loss or maximize the likelihood. And then we mentioned this many to one. So there was a multiple output here and a one output here. Yeah, but the idea is basically the same. And now for training, there is backpropagation. But basically you unfold the computational graph, and you let the flow backwards the gradient, right, through time. And one problem is that this could be very long, right? And for stability reasons, and to partly mitigate the problem of vanishing gradient, people tend to limit the sort of time backwards that you do the computations, right? And that's called truncated backprop. And then on top of that, you use the things that we mentioned before. A problem that we appeared before, which is the vanishing gradient problem. Actually, we have two problems here. One is the gradient vanishing, which was mentioned before, is the same. And here now we have a possible gradient explosion. And the idea is here, sorry, is that as we go backwards, I mean, the sort of flow in backprop, we need to go backwards. So there's like some kind of flow of the gradients like this, right? And at this of this, there's a sort of multiplication of these weights of this matrix, right? So right. And the idea is that I mean this matrix explodes, basically controlled by the first eigenvalue. So basically, if the biggest eigenvalue is bigger than 1, there's gradient explosion. If there is, if it's smaller than 1, the gradient vanishes, right? And basically means that well, this is unstable, and this on the one hand, this doesn't learn, and there is it forgets more and more the what happened long term, which was one of the things that we wanted to avoid. So. Some people provided solutions to this problem, which is gradient clipping, for example, which is you put a threshold, and if the gradient, then you truncate it to whatever. And for this, there's these two alternative architectures, which are quite important from the let's call it historical point of view, and that's how we finish today. Talking by this. So these were, as I said, these were like super cool until, let's say, 5 years. For example, Siri you use is basically based on that. And this is one of the sort of heroes of the scene. Actually, this is one of the. He is one of the persons who says that he has discovered. I mean, you say something and he says, "I discovered this like 20 years ago," and he has several people like this. So it's like Mike West, but in neural networks. Okay. So that was introduced in 1997, but only used until relatively recently. And the idea basically is that this, which was a graph for the recurrent network, is replaced by some type of structure that it will contain as something. I mean, it would actually have like two hidden pieces of information. Right, we'll see in a minute. But one of the pieces is more or less like as before, the hidden state. But the other state is a cell, or it's a memory. It's a memory, right? So that's the key difference. So these were the recurrent neural networks that we mentioned before, Ellman's model, right? And this is being replaced by this guy. So you can see that here there was just one path, and now there would be like two paths. One will be taker and will provide the hidden state, and there's another one which is called the cell state. It's another memory, and that's the one. This will have two advantages or two reasons. The first one is that this cell state will take care of the memory, so it will preserve the memory here. Here, I mean, if you remember here, the H state was rewritten. It was rewritten each time, right? So this provides like a more permanent memory, and therefore it will allow the network to remember things from a later time, right? From earlier time, right? That's one thing. And the second thing is that remember that before this one, the gradient was following this path. and therefore was either vanishing. I mean, quite frequently it was either vanishing or exploding. So this flow, in this case, the flow of the graph, because it's how this is conceived, it will allow this like information flow in this, it won't explode or won't vanish. And that would be the other advantage. So just, I mean, it's not super important to think of the, but we're going to explain briefly, because it contains ideas from memory and attention that will be used for the next week. So, well, these are the sort of, I mean, this will be a new way, and well, gates, it's our computational gates, computing gates. So the elements are here as before, the entrance of the new data and the hidden state. These are somehow combined to something which is called the forget gate. I mean, this is going to be a factor which basically will say, I mean, it will go to this memory, right? And it basically will say how much do you forget of the current thing, right? In this case, I mean, the functions that they propose are a sigmoid, right? Applying to this thing. So as before, it's a matrix which is multiplying this vector plus a bias. One thing to understand a little bit better, I mean, remember that sigma goes to from 0 to 1, and then if you want to try to understand it better, try to think of what happens when it's 0. I mean, when it goes to 0, and what happens when it goes to 1. So the second element, the second part, it refers to the, I mean, it will be like the info gate, which basically says how much input, how much information is going to store in the cell state. You can see that these are two components that will appear here. I mean, C is coming here, and it will receive this input here. And basically, this has this is basically how much are we going to perturb the memory. And now this is a tanh, so this is it goes from -1 and 1, and you can think of what happens when this goes to -1 and when this is a 1 exactly. And then this tanh is a nonlinear fraction. The operation is the same. We are multiplying another matrix to this vector. Again, is the hidden state plus the input now plus a bias. Now we update the cell state. So this was the forgetting thing. This is how we update, and basically the memory is the previous memory. How much do we forget it? What part do we forget it? And how much do we input? I mean, what's the new input to be included? And then finally, the new hidden state. Again, how much do we decide to output, right? From that would be the sort of intuition, and that would be the new hidden state, right? Again, that would flow for the next, and that would be used. That would be used for whatever purpose. I mean, predict the next word or whatever. So these are everything put here together. Yeah. And then there was these LSTMs. There's several variants. One of them was the GRU, the gate recurrent unit, which basically has similar contents, right? In this case, there's just one hidden state, which takes into account what happened. It's a sort of linear combination of the current hidden state and the innovation. But the computations are very similar, and computationally are quite similar to LSTMs. Okay. So we are putting a lab in R at the GitHub site. If somebody, the rest will be in Python. I'm old, and the younger people will do Python. But it's kind of interesting. Keras, you can use it in, but it's just to illustrate that you can use the embedding layers included. You can use LSTMs and then mix with other dense layers. Let's call them classical R recurrent neural networks in Keras, in R, but in Python as well. So there's simple RNNs, are Ellman's model, but you have also layers for LSTMs and GRUs, bidirectional layers, bidirectional LSTMs, and also there's one-dimensional convolutions, which were convolutional networks which were used. It has also text tokenizers. There's also layer embeddings, and then you can use sort of standardized embeddings like word2vec and glob. So there's plenty of things that you can use if you need to do this. But this is actually kind of old. So we go next week to transformers, and that was the sort of very nice marketing. Attention is all you need, right? And we'll do it next week. And these are the readings that Roy will send them by email, right? Next, in one of these days. But basically, there's some videos on, let's call it transformer for poets. And actually, you can actually use transformers or ChatGPT to do poems, right? As you probably know. But transformers for poets is transformers for something like me to be easy to understand. But then there is this paper which is it's quite important. It has an annotated version with code back to back, which is kind of interesting for those who like coding. And then a sort of more, let's say, high level. Let's say more, I would say more, this is like a more informal, but it's slightly more mathematical, but very well, nicely explain the formal algorithms for transformers. And then there's these are accompanying resources for computing. And I think that was what I wanted to talk. That's it. Right. I don't know if you want to make questions or any other instructions, or I don't know.
There is questions in the chat, but people outside can unmute and ask, because we are all gonna listen.
Right.
Or if anybody has questions here.
Those these are questions already, or?
I had a question regarding the Bayesian analysis of neural networks. So in the paper Current Advances in Neural Networks, there was this showcase of fully Bayesian analysis of networks. And I wanted to ask, how successful have they actually been? And also if this has been extended to deep neural networks.
Yeah, so that's a good question. Actually, the paradigm, the predominant paradigm is maximizing likelihood plus a regularizer, which you can view as an approximation of the maximum a posterior thing. But there's a community which is growing and says that some of the mistakes that we shall mention over these days, some of the sort of problems that you find with, let's say, classical approaches to deep nets can be solved through Bayesian approaches. I would say, I mean, some of the things that you can do is a better characterization of uncertainties, which is quite important if you are going to use these predictions to support decisions, right? That's the first one. There's another one which is also quite close to our heart, which is they tend to be more robust against attacks. And to some point, you can it can help for interpret and explain. But on the other hand, there's an obvious problem, which is the computational issue that needs to be solved or needs to be improved. So I mean, I think there's a growing community in computer science which is promoting this Bayesian approach. One of the papers that we put, have we put the whole list of? No. Well, there's one. Well, yeah, I think it's called the manifesto. No, Bayesian manifesto, whatever. There's a manifesto asking for this, especially in large language models. But I think I mean, it's not computationally efficient. I mean, the approaches are not computationally sufficiently efficient from a computational point of view.
Okay, thanks a lot.
And one of the reasons for doing this thing, I don't know, it's so nice that you could probably be playing tennis or whatever. But one of the reasons for us for being here is that question that you just made.
Okay, thank you.
So is there any intuition why the Bayesian approach is more robust?
Yeah. Well, first of all, it's more difficult to attack one of these models because you have uncertainty about the parameters, right? So what I call white box attacks wouldn't be possible, right? Because the guy doesn't know the parameters. So that would be the reason.
Hello, good morning. Jorge here from the Israeli Institute of Technology. I would like to ask, because one of the things on large language models and one of the main issues, especially in generative models, that it's been happening a lot lately as they keep evolving, is hallucination. So what do you think will be like the major focus from the mathematical point of view in order to deal with hallucination in large language models and generative models?
What do you want? Well, I think it's more. I would say it's more control of the prediction. I mean, if you have more control of the uncertainties, you have more control over the predictions, and therefore you have some control over these hallucinations, I would say.
Okay, thank you. I mainly did this question because the latest approaches for generative training models and large language models are to be trained while the user is actually inputting data or inputting information. So it gets feedback from the user that's using it also. And sometimes that can lead to like dark places, say it that way.
Yeah, we're going to cover partly, Victor is going to cover partly, and he's an expert on that. He's going to cover this human feedback thing that you have mentioned, and I think it's in day 4, right? Or day, yeah.
Okay, wonderful, thank you so much.
Okay, I hope I'm not interrupting anyone.
No, no,
By the way, David, my apologies, and also to the rest of the audience. I speak a little bit low today. Just didn't sleep much. So just in case you don't catch anything, just tell me, and I will, try to
Yeah.
speak a little bit louder.
Actually, it's not your problem. It's my problem
Oh,
because
okay.
I have. Actually on Monday they will remove my. I don't know the word in English.
Yeah.
Oh,
Yeah.
so it's better if I put this way.
Yeah, my apologies. In any case, I will, I will try to speak a little bit louder. So I just had, first of all, just a very small remark and then a couple of general considerations. I will try to be as concise as possible. So what you explained, about long short-term memory, so I think this is, of course, it's quite a complicated concept, to come up with because you have to be, quite ingenious, to come up with such idea. But but I think actually, for me, if this is my perspective at least, if you incorporate, some elements, from optimal control theory and from dynamic programming, then it becomes much easier to understand because, from what I understood, essentially, really, I mean, what you're doing is basically you're trying to control for either gradient vanishing or gradient explosion by introducing, some kinds of small amends, at the appropriate moment, in the whole line of input. So this will be, so I think, it becomes easier basically, to understand, if you see it more, from the perspective, of dynamic programming and optimal control theory. And then, just a couple of very brief considerations. First of all, I'm not exactly sure, if this is more a matter, for these reading sessions, because
What, sorry?
reading sessions, reading book.
Really?
Yeah, okay.
The 5 sessions, we have, because they're quite concise, or more for the working group, that we are planning to organize later. But anyway, what I wanted to comment a little bit, and I will be very brief. You commenced your presentation, by mentioning AI hype and AI hype, okay, and actually,
Well, I said that because even President Sanchez on Friday talked about
Yeah.
it. So.
Exactly. Exactly. This is my point precisely. And so, because, I have been studying, artificial intelligence history, quite a lot, namely, there is a wonderful book on this by Niels Nilsson, the quest for artificial intelligence, with which I suppose, most of you are familiar, and I actually, for me, the problem was not so much, and this is something that I fear also, at the moment. So for me, the problem is not so much necessarily, in the technical limitations, because there were some, extraordinary scientists. For example, I mean, Marvin Minsky, Herbert Simon, John McCarthy. But the problem, was actually more, in my perspective, it came out of the bold statements, that they made and that contributed, to create, sort of unrealistic expectations.
Yeah, okay.
You know what I mean?
Yeah.
So, for example, John McCarthy, as you may recall, in the conference of Dartmouth, in 19, for example, he said that the whole theme of artificial intelligence will be resolved in 6 weeks. Then Marvin Minsky in 1970 for Life magazine, he said the same thing, but only changing weeks for, years. And that, what worries me is this lack of delineation, I'm going to conclude just 30 seconds. So what worries me a little bit, is this lack of delineation, between, the enormous practicality, for example, of large language models and the lack of delineation between these and what artificial intelligence actually is about. And then, the very last point, that I wanted to mention is also, and I would like to upload, a couple of papers. I actually asked Roy about these to Google Groups, also on the limits of scalability. Because, for example, Dubron, for example, I mean, he has been speaking about this a lot, challenging the approach of, for example, Hoffman or Kaplan, and so basically scalability, it has its problems and it has its limits. I'm sorry if I have been too long. My apologies.
Yeah, but I have I have short memory and long memory. So
Okay.
even if I'll be a little bit deaf, don't worry.
Yeah.
We're gonna talk. I mean, scalability will appear, and I would say Good that you pointed out a historical thing. But I think, this has some ups and downs, right? But I think this is a definite one. I think will stay with us, and
Yeah.
I mean, this is
Mhm.
definitely.
Mhm. Mhm.
But there's a hype. I think. Okay. Any other comments or nothing on the chat or?
Well, they were discussing whether embeddings are learned or not, and I think we can. I mean, we will talk about that in the next session.
Yeah, next session. Yeah. Okay, so thank you.
Sí,